Alright, so in this lecture, we'll continue the part 2 of transition elements. So in this lecture, we'll discuss constitutional isomers of coordination compounds. So let's discuss what is an isomer. So isomers are compounds that are similar in connectivity or in optical activity. So these are called isomers in general. So there are two types of isomers. So we can classify isomers into two types. So one is constitutional isomers and second is optical isomers. So let's discuss in this part constitutional isomers first. So constitutional isomers are molecules with the same molecular formula but differ in connectivity. So here connectivity refers to the atoms, differ in connectivity of the atoms. So these are called constitutional isomers. Now there are two types of constitutional isomers. We have coordination isomers and we have linkage isomers. Coordination isomers occur when the composition of the complex ion, occurs when the composition of the complex ion but not the compound is different. So this can happen when there is an exchange of ligands and a counter ion or by the exchange of ligands. So the other one is linkage isomers. So these occur when the composition of the complex ion is the same but the ligand donor atom is different. So some of these ligand atoms can bind directly through the metal through either of the two donor atoms. So the difference here is that the difference in the linkage, here the difference in the ligand itself. Let's take an example of a linkage isomer. So in a linkage isomer, you have a compound, you have, this is CONH3 taken 5NO. So this is the part of the complex ion, this structure. Notice that here, this NO2, in this, the nitrogen is the one that's connected. Here also, the internal structure is still the same. So the internal ion, the complex ion is still the same. But here, the linkage is not with nitrogen, but with oxygen. So you have NO2, here you have ONO. So this is an example of a linkage isomer. So the one with NO2 is called as a nitro isomer. The one that bonds with oxygen is called as a nitrate isomer. This happens in monodentate ligands which have more than one donor atom. So if you have one or more donor atoms, then this is the structure, this is the type of isomer that you will end up with a linkage isomer. So ligands that are having more than one atom is nitrate, cyanate and thiocyanate. So whenever you see cyanate, it's oxygen. Whenever you see thio, remember that it's sulfur. Next, let's look at optical isomers. So the other name for optical isomers is stereoisomers. So we can classify stereoisomers into two types. One is geometric isomers, the other is optical isomers. So geometric isomers, the other name for geometric isomers is cis-trans isomers. So here, what is a stereoisomer first? So stereoisomers are compounds that have the same atomic connections but different arrangements. So the one might be in the left side, one might be on the right side. So they might have different spatial arrangements. So spatial is the directions. So the directions in which the attachments are might be different. Now, what is a geometric isomer? So geometric isomer is when the atoms or groups can be arranged on the same side or on opposite sides of the compound relative to the central metal ion. So those are called geometric isomers. Optical isomers are basically non-superimposable mirror images. So an example of an optical isomer would be your left hand and your right hand. So if you take your left hand and right hand and put it next to each other, you notice that if both of them are mirror images of each other, but when you rotate it and keep it in front of you, they are not actually similar. This is an example of a non-superimposable mirror image. So a non-superimposable mirror image is when the mirror image and the image are not the same. So the mirror image and the image are not the same, so we call them optical isomers. Now, let's take an example of a geometric isomer. So if you consider here, this is the platinum metal ion, and you have two chlorines, and you have two NH3 molecules. Notice that both the groups here are on the same side, the same group are on the same side. So those are called cis isomers. If both groups are on opposite sides of the axis of the metal ion, so to classify this, what we'll do is we'll cut the image in half through the metal ion, and on each side we'll judge whether the similar groups are on same side or on opposite side. Here similar groups are on opposite sides, so we call this a trans isomer. So in a cis isomer, identical ligands are adjacent to each other. In a trans isomer, they are across from each other. So best example of this would be this compound in itself. Why do we need these isomers in general? Because isomers in themselves can act differently in terms of their chemical reactivity. So this compound is called as a platin. The cis isomer of this platin is an anti-tumor agent, but the trans isomer has no anti-tumor effect. So this is the reason why we have geometrical isomerism. Another example of a geometrical isomer here would be to look at the axis. So if you take this compound here, if you take the central metal ion, how would you classify them based on their placement? Is look across each of these ions and see if you take in each bond, if one of them dominates where they are on the opposite sides. So if you see the linkages across the metal ion, notice that in two of them they are on the identical molecules, but then the other two you have identical groups on each side, so that's why it's a cis isomer. But if you take the axis here again, notice that these two are on opposite sides of each other, so that's why this becomes a trans isomer. So this is how you can notate a cis isomer and a trans isomer. So next is optical isomerism. So optical isomerism is the mirror image concept. So if you take these two images, these two are mirror images of each other, but when you take these two are not mirror images of each other. So these are called optical isomers. In the same way, if you take these two are mirror images of each other, but the connectivity between these two is not the same, so they are not optical isomers. So they are only optical isomers when they cannot be non-superimposable. So we can classify constitutional isomers as coordination isomers and linkage isomers, stereoisomers as geometric isomers, and optical isomers. So geometrical isomers, the other name for geometrical isomers is diastereomers. The other name for optical isomers is enantiomers. Now try this structure. So I'm going to do one, so you can try the second one. So let me try the first one. So here they're asking you to write down the entire structures, every possible isomeric structure. So this is the structure, and they've given you that this is a square planar structure. So in a square planar structure, you have platinum in the center, and you have groups on all four sides. So to differentiate this structure based on which is in the front and which is in the back If something is on the front, we write it as a wedge shape. If something is in the back, we write it as a dashed line. So we can convert this structure as platinum. So we consider that the ones that are in the front are on the down, and these are structures on the back side. Now, we consider NH3 and Br2. There are two chances that can happen, where NH3 can be in the front and both Br can be in the back. So this becomes cis PT, NH3 taken twice, Br2. The trans structure for this would be where NH3 is on the front and Br is in the back. You have NH3 on this back and you have Br. So notice that here both NH3s are on the same side, Br is on the back side. So this is an example of a cis isomer. Here NH3 and Br are on the opposite side. So that's fine. So because we are considering this axis, so this becomes a trans PT NH3 taken twice Br2. So this is the structural conditions. So what are the types of bonding in the complex ions? So when a complex ion is formed, each ligand here donates an electron pair to the metal. The ligand acts as a Lewis base, basically meaning that it acts as an electron pair donor. But the metal ion acts as a Lewis acid, meaning that this acts as an electron pair acceptor. So this type of bond is called as a coordinate covalent bond. What is the difference between a coordinate covalent bond and a covalent bond? If you consider a covalent bond, for example, if you have carbon with 4 carbons, for example, let's consider that oxygen with its 2 lone pair of electrons, there is another oxygen with these 2 lone pairs. These two like to share those electrons, so this donates its electrons and this oxygen also donates its electrons, so that results in oxygen forming double bond. In a coordinate covalent bond, only one atom donates electrons. So best example of this would be if you consider a structure of BH3 and NH3. NH3 here has a lone pair of electrons, so this donates it to BH3 and then forms BH3 bond NH3. This bond here is a representation of a coordinate covalent bond. So what type of hybridization would you see here? So the common hybridizations that we generally see are sp3, sp3d2, and you can also see esp sometimes. So what type of hybridization would we generally see? So let's take an example of this atom, chromium hexaammoniate. So this is hexaamine chromate. So let's take this atom, CrNH3 taken 6, 3 plus. So here you have a chromium atom which is 3 plus charge. So chromium here has an atomic number of Z equal to 24. So when you draw the table, you get 4s, you have 3d, so you have 3s and 3d. So the s orbital has 2 electrons and the d orbital here has, it's 24, so we have argon 3s2 3d4. so it has 4 electrons here. But I told you that chromium has a peculiar characteristic where it does not fill the s orbital, but rather fills the half-filled d orbital. So it half fills everything. So this results in all of them having 1 electron each. So now what happens? Chromium, when it becomes Cr3 plus, loses its 3 electrons. So when you consider that if it was originally just chromium, then we could have half-filled orbitals, but chromium here is losing electrons. So I already told you that it loses electrons first in the s orbital, so it loses electrons here first, and then it loses 2 electrons there lost, and then there's another electron here. Now for just Cr3 you have 3 electrons in the d orbital, and we can consider the next orbital as well. The next orbital here is 4s orbital and the 4p orbital. So what happens in this hybridization here, in sp3 hybridization here, is that it combines the rest of the 3d orbitals, the 4s orbital and the 4p orbital. So you have 2 of them here plus 1, and from the 4p orbital you have another 3. The combined here of s, p and d, where s donates 2 electrons, it becomes s, p, p3, and then it donates 3 pairs, and d has 2 pairs, so it forms sp32 hybrid orbitals. So the combined orbitals then form a 6 series of orbitals. So this is 6 sp3 d2 hybrid orbitals. Each ammonia has a lone pair of electrons. So those lone pair of electrons go into each of these hybrid orbitals. So that then results in 6 electron. So 6 electron pairs from 6 different ammonia atoms. So you have 6 of them that are filled in each of these shells. So that's where it forms the coordinate covalent bonds, resulting in chromium hexamine chromate. So this is how the structure originates, and this is where the hybridization works. Notice that the hybridization here is happening with the empty orbitals that are after 3D. So this is where the structure relies on. When you take the same structure for NiCN4, cyanide, nickel, so you have nickel having Ni2 plus charge, so that results in 3 lone pairs. Nickel originally has an atomic number of Z equal 28, so you have argon 3s2 3d8, so it fills 3 pairs with 1 electron each, and when it becomes Ni2 plus, it loses these 2 electrons. So what happens now is that it combines the 1 orbital that it has, and it combines everything else. That results in an sp2d hybridization. Those sp2d, you have 1s orbital, 1d orbital and 2 p orbitals. So that creates 4 different sp2d hybrid. So that bond to 4 different sp2d hybrid. So remember that when it forms an sp3d2, the structure is octahedral. For sp2d, the structure is square planar. So then when do you get a tetrahedral structure? You get a tetrahedral structure when it forms sp3 hybridization. So that is the next structure, which is for ZnOH taken 4. In zinc has no d orbitals left, so the orbitals taken are the next orbitals 4s and 4p. You have 1 4s orbital and 3 p orbital, so it forms sp3 hybridization. So 4 OH ions donate each electron pair and then form sp3 hybrid. So when it has sp3, the structure forms a tetrahedral structure. So this is the summary of the structure. So at what time do you get what structure? If it has sp3d2, you have 6 bonds and 6 ligands. That results in an octahedral structure. If you have sp2d structure, you form 4 bonds with 4 ligands, and that creates a square planar structure. And if you have sp3, you still form 4 bonds with still 4 ligands, but you end up with a tetrahedral structure. So here the angle between each of them is 90 degrees in the equatorial direction and 90 degrees in the axial direction. In square planar, the angle is 90 degrees. In tetrahedral, the angle is 109.5 degrees. So this is the angle and the structure that determines, so the hybridization determines the structure that is obtained. So the next topic is the crystal field theory. So crystal field theory basically explains why transition elements end up with color and magnetism and the effect of ligands in creating the color and magnetism. So the bonding of ligands to the metal ion cause the energies of the metal ion in the d orbitals to split. So how would the splitting of the d orbitals occur? So splitting in general, you have a 3d orbital with 5 different pairs. This 3d orbital, when it bonds with ligands, it reaches a higher energy because of the extra electron. Then this again splits into 2 parts, one with a lower energy, one with a higher energy. So 2 of them go to higher energy and 3 of them go to lower energy. The 3 of them that go to lower energy are dxy, dyz and dzx. And the ones that go to higher energy are dx square minus y square and dz square. So this, the energy difference between the last split between these 2 orbitals is called delta. This energy is called as the splitting energy. So this energy is called as the splitting energy. And this is the energy that can determine the color and that can also determine the magnetic behavior. It can also determine the magnetic behavior. So this splitting energy is also called the crystal field splitting energy. So this delta energy is called as the crystal field splitting energy. Now, when you have a weak ligand, the ligand or weak field ligands, they are weak field ligands when the splitting energy is small. You have a strong field ligands when the splitting energy is large. That is determined by the ligands that we use. So weak ligands result in smaller splitting energy and strong ligands result in larger splitting energy. So how would you determine which are weak ligands and which are strong ligands? So how do you get the color of titanium here? Titanium hydroxide, titanium, so hexaqua, titanate has a splitting energy of a really small amount. So the amount of light that passes through this energy determines what light passes through this. So here the gap is only left for green and yellow. So then in the second part, it's absorbed and then transmitted. So what happens here is that whatever is the energy split, that energy is absorbed. Whatever is the rest is left out. So what is absorbed is what the combined color looks like. So here it absorbs green and yellow. So the combined color gives you a purple color. Now the colors of the transition metal complexes can be determined by the crystal field splitting energy of the complex ion. So for any given ligand, the color depends on the oxidation state of the metal ion. So the color depends on the ligand. Now, if you consider vanadium hydroxide, where the oxidation number is 2 plus 2, it has purplish color. When it is plus 3, it gets an yellowish color. In the same way, if you take chromium hexamine chromate, so it results in a yellow color, where the chromium has different chromium has 3 plus oxidation number. If it has a 2 plus oxidation number, it turns a little more pinkish. How to determine the spectrochemical series? So the more the charge on the ligand, the weaker the field ligand. The more as you go from iodine is the one that is the weakest field ligand, you go to copper monoxide, which is the strongest field ligand, and it results in a smaller wavelength, smaller energy to a larger energy. So, and you go from a longer wavelength to a shorter wavelength. So as you increase the delta value, you start seeing shorter wavelengths of light and must be absorbed to excite the electrons. For example, H2O here is considered a weak field ligand, and in consideration NO2 minus is considered as a strong field ligand. So let's compare here between titanium, where you have H2O ligand, NH3 ligand, and CN ligand. Now we are ranking them based on delta and energy of the visible light absorbed. Now let's look at each of them in this diagram. Now we are talking about these three compounds. So we are looking at H2O, NH3, and CN. So in place of splitting them in terms of delta, we are looking for the smallest delta value to a largest delta value. So in the series, H2O is first, next you get NH3, next you get CN. So TiH2O, so here we can write H2O is less than NH3 less than CN minus. So this is for delta. In terms of the next part, which is the energy of the visible light absorbed, so visible light is absorbed more when you have a lot larger a structure. So the same thing happens here as well. So you end up with a smaller, larger delta to a shorter delta. So more energy is absorbed by the shorter delta region, so because it's a stronger field than a weaker field. So this is your final answer. Now, how do you classify the magnetic properties? So magnetic properties are determined by how excited the electrons get. So if you look at a general manganese atom, Mn2 plus has about 5 free electrons. When it's a weak field ligand that comes in, when you take MnH2O, the splitting energy is smaller, so it has a high spin complex where the electron jumps easily from one orbital to the other. So it's easy for the electrons to jump from a lower energy orbital to a higher energy orbital, so it goes from here to here. But when you have a strong field ligand, let's say for example CN, it results in the electrons not able to go to the higher orbital, resulting in the electrons staying at the lower orbital. So this is the energy called as the energy of the pairing. So if the pairing energy is greater than the splitting energy, that results in a higher magnetic field. If the pairing energy is less than the magnetic energy, this will be, if the pairing energy is less than the splitting energy, that results in a stronger field. So again, here you have D4, where high spin results in a weak field ligand, where it's easy to jump from one orbital to the other. But here, when you have a low spin, strong field ligand, you notice that the electrons cannot jump from a lower orbital to a higher orbital easily. So try this problem and see if you can work out between these two systems. So one last topic to discuss is, why do we need these transition elements? One common connection is the concept of hemoglobin and most common essential enzymes and vitamins. Most common essential enzymes and vitamins generally have a metal ion in the center, and they are generally complex ions. So most of them are complex ions. So a best example of this is hemoglobin. Hemoglobin has a central compound which is the main active compound, which is heme. Heme contains a small iron molecule in the center. So best example of this would be this structure. So here this is the protein heme. So everything that you see here, these are alpha proteins, right? And I want you to focus on this ligandic structure. So this structure, in this structure, this is the iron molecule. So this is the iron molecule Fe, and all of the other structures that are connected to them form the molecule. So this is what carries oxygen. So this is what carries oxygen. This is the central ligandic molecule that can carry the oxygen. So these are some of the common compounds. Another example of this comes, so you'll see that each hemoglobin has multiple ones of these. So this is the general structure that you will generally see for any general compound. There are multiple of these. Best example of them are vanadium in proteins that are used in redox couple, as a redox couple in fat metabolism. Chromium is used as a glucose tolerance factor, and its used is to utilize a lot of glucose. Manganese is used in an enzyme called isocitrate dehydrogenase. It's used in cell respiration. Iron is common in hemoglobin and myoglobin, cytochrome C, and catalase. In hemoglobin, it's used for oxygen transport. In cytochrome C, it's used for cell respiration and ATP formation. In catalase, it's used for decomposition of hydrogen peroxide. And cobalt is the compound that's found in cobalamin. Cobalamin is vitamin B12, so that's the one that is found there. And it's used in the development of red blood cells. Copper is used in two different enzymes. One is ceruloplasmin and cytochrome oxidase. Ceruloplasmin is used in producing hemoglobin. Cytochrome oxidase is used to produce in cell respiration and ATP formation. Zinc has multiple uses. It's also used in an enzyme called carbonic anhydrase, which is used in the elimination of carbon dioxide. Carboxypeptidase A, which is used in protein digestion, and alcohol dehydrogenase, which is used in metabolism of ethanol. So it helps us in understanding how these metal traces that are present in our body can help understand the common essential elements that we generally use. So this is the reason why we end up taking a lot of these from natural foods. Sometimes we end up taking it as supplements. Sometimes we end up taking it as a natural food source.